The opinions expressed in the following program are strictly those of the speaker. They do not necessarily reflect the views of the National Science Foundation.
From the National Science Foundation, where discoveries begin. This is Frontier, discussions of today's most exciting research subjects by distinguished scientists and engineers working at the frontiers of knowledge.
Many examples of complex networks that have greatly impacted our lives, such as highways and the internet, derive from engineering. But although engineers may have developed the components, they did not plan their connection. How can engineers who have developed many of the most important complex systems stay connected with their subsequent development? Complexity and engineering seem at odds. Complex systems are about adaptation, whereas engineering is about purpose. However, it is robustness and failure where both camps merge. In the following presentation, Engineering Complex Systems and Complex Systems Engineering, you will hear how engineering can benefit from incorporating complex systems tools in its standard toolkit. Northwestern University's Dean of Engineering, Professor Julio Ottino, presents the case that complex systems offer opportunities for paradigm shifts in established research areas, and even the creation of new disciplines in engineering.
A lot of what you will hear about complex systems did not originate from one birthplace and then kind of diffuse with one dominant school of thought in mind, but there are lots of places in which it started kind of independently, and the idea is how do you kind of collect things and present a unified vision when in fact there are many, many, many different visions. So what I'll try to do is take a high altitude view. I don't think I am selling one particular aspect of this, so I think I'm pretty objective on this. But I'll try to give you a broad perspective. I'll try to define things like what's complex and how it differs from complicated. I'll try to give you a sense on how this could impact disciplines and how there may be hurdles for the integration of disciplines, how this may create actually new disciplines. But let me start by first explaining the title. When I say engineering complex systems, the word engineering there functions as a verb. Okay? Means you want to engineer a system. When you say complex systems engineering, that will mean that there could be books and courses. That will mean that you got the discipline. It's two different things. We don't still have the discipline completely shaped, but we actually can do a few things on the engineering complex system. So along this talk, I even will descend to the point of saying what engineering means to me, because I think it's part of the picture in presenting this broad view. So engineering complex systems, engineering as a verb, and we can make something work even if that requires to fill the missing science parts with heuristics. In complex systems engineering, we got the discipline, we got the set of tools. Now, there will be examples that will appear in here ranging from how neurons are connected in the brain, to schools of fish, to organizations. I came to this from much more humble origins, okay? Those little balls bouncing up and down at the bottom, which is granular matter. And I'll give you kind of 2 or 3 slides on this. First, that you can gauge what has been my angle on coming to this, and also because it's probably the simplest possible example of some things that represent what we'll be talking about. So what I have in there at the top is a long cylinder, could be this long, filled halfway with particles of 2 different sizes. okay? And the cylinder will rotate. And the particles are, the small are black and the large are transparent. So when you rotate this, and this is a highly accelerated movie, this is what happens. It seems like a violation of entropy. The particles spontaneously split into domains. And if you look at this, do a time kind of plot, there you have it again, and you'll see that domains sort of disappear, it constants. So you do a time plot, you see something like this. This is still an open question as to how this happens, okay? And if you do experiments involving the same thing, and the particles could be in air or in a liquid, the tube could be a circular cross-section, could be square. This happens all the time. So in here I'm showing the same system at different speeds, and you have to be very fast to catch up what's going on at the top two, and the bottom two, things will be much more relaxed. And this is what happens in here. Remember, there were two classes of particles, large and small. In a tube, you just spin it, and this happens, okay? And if you do a time plot of this, what you get is all of this. So how come little particles, which are more or less all identical except in two categories of size, can do such a complicated stuff? But there is some regularity in here, and you can extract statistics from this, and they are pretty well behaved, and I'm trying to show some of those on the right-hand side. But when we were doing this, and I debated whether or not to hook up directly to the web and showing demos in here, but I can still, since you never know whether or not you can connect or not, I'll show you snapshots of a couple of demonstrations. This is a NetLogo simulation. NetLogo is a language which is largely now developed by Uri Wilensky in our institution. And if you go to the NetLogo website, you will find like, I don't know, 200 different toy models to work with. This toy model is basically a city, okay? And there are two kinds of people in this city, the red people and the green people. And they both have some degree of tolerance on how many neighbors of different colors they will accept living next to them. And you can put that and change that in the cursors on the upper left. And when you do that, the program will evolve in such a way that everybody is happy at the end. And probably that will entail that in between red little neighborhoods and green little neighborhoods, there has to be black little spaces. Those are empty spaces. So in here, what we are putting is that the degree of tolerance, people are willing to live with 55% of people who are equal to them. And you can change this. But by the way, this NetLogo program is a program that is a low threshold program. My kid has programmed in this, but no ceiling, in the sense that you can do complicated stuff, okay? So when you let the program run, this is what happens. And the question is, how come if people were more or less, they didn't care, 55% is pretty tolerant, how come these end up so segregated? Now, the fellow who did this, I was alerted to this, I don't know, probably about 10 years ago, was this fellow Thomas Schelling. And when I heard the name of the book that he had written, From Micromotives, the micromotives being the tolerance, to the macro behavior, I was really amazed. And I could see connections with physics and with my granular stuff. Now, Schelling was an interesting character. And in the back of the book, he says, through familiar and readily grasped examples, Schelling demonstrates what happens when behavior in the aggregate is more than a simple summation of the individual behaviors. How members of a society tend to be blind to the collective consequence of their separate decisions, and why attempts to infer individual intentions from group phenomena are tricky at best and often downright impossible. This is probably the best example, simple, of complex systems, is collective behavior which we cannot infer by looking at individual pieces. Now, Schelling won the Nobel Prize in Economics for this and other things. He was in Harvard, then I think he went to Maryland. Very bright fellow. So complexity, in some sense, is not that the pieces have to be complicated like in chess. It could be more like the game of Go, in which the pieces are themselves very simple, but the behavior that they display on the aggregate is complex, which I'll try to define in a second. Now, the word complex itself, without getting into Freudian and what complex means in psychiatry and things like that, has lots of different meanings. The word complex, as signifying composed of many parts, is old. It comes from the 1650s. And the meaning as an adjective, meaning not easily analyzed, is from the 1700s. What we understand now by complex comes close to these two things. But what I'll give you is a sort of, we can debate until midnight about possible definitions. I'll give you two, because at the end of the day, I don't think that the definition is the most important thing that you have to agree on in the context of doing something in the area of complexity. But I'll give you these two sort of operational definitions. You have something in front of you. You can attach the label complex, first by looking at what it does, and if it displays organization without any organizing principle being applied, from the top, the behavior emerges, you will call it complex. In that sense, the granular stuff, in the way that sort of puts together, does that. The Schelling city does that. Or how it can be analyzed, decomposing the system and analyzing a part which has served us extremely well since the time of Galileo, okay? That's not working here. I mean, you know everything that there is to know about the individual in that city, and you cannot predict a priori what is that is going to happen. So if you want to encapsulate this, is rich behavior with simple parts. Now, how does complex differ from complicated? This, I'll give you my take on this. Everybody would understand what simple is. A pendulum, 2 billion boards hitting each other. Complex, I put the school of fish or a market. Complicated are systems that consist of many, many parts, like the Boeing, the jumbo jet in there, or the Patek Philippe watch below. Thousands, probably even millions. But each part in a complicated system has a strictly defined function that was sort of put in there by the designer. Okay? And the parts in general do not adapt. So there is a failure on a critical piece, and the whole system collapses. In an ecological system, you can have fluctuations, and as long as they are not extremely large, the whole system will adapt. So that's a definition of complicated and complex. It doesn't have to do with the number of parts. The number of parts in a complex system can be all identical, like the school of fish in there. The question is, how come they decide to adopt the configuration in there? But there is adaptation, okay, of the pieces. In a complicated system, the pieces have fixed roles. So some possible questions just with this. Can we guide systems that want to design themselves? Is it possible to design elements with built interactions so that the systems design themselves in some kind of intelligent manner? Or given a final picture, can we uncover organizing roles? So when you ask that question, for example, one subject that appears in the picture is material self-assembly. We know what the basic interactions are between atoms. The question is, can we predict what structures things will produce? And that's a very difficult question. So I mentioned the word engineering as a noun and as a verb. But let me give you kind of get back in here and give you the definition of engineering itself according to me. Okay? Well, I'm going to quote someone in here. If a situation is complex and poorly understood, and if the solution is constrained by limited resources, could be knowledge, then you are in the presence of an engineering problem. Now, when you define it in this way, everybody is an engineer, and engineering is the oldest thinking, organized thinking structure in the world. To be human is to be an engineer, in the sense that you are facing problems that you have to solve without probably have all the elements in peace. Roman engineers were building aqueducts before the laws of statics were firmly established. You fill the gaps. So the question is, can you engineer complex systems even though there may be gaps in the knowledge? And the answer to that is partially yes. So what are the tools that are contained in the engineering toolkit? My contention is that there are 4. Nonlinear dynamics, which by now is all had. Chaos theory will be there. Broad-based statistical mechanics, and I will have something to tell about this, including some historical remarks. Agent-based models, which were the ones of Schelling that I showed before, the net logo thing, and network theory. Nonlinear dynamics. So very quick, this is where I came from. This is how you make sense of things like this. Little spheres on a plate, you vibrate the plate up and down with a frequency. This example comes from Harry Sweeney in Texas and Paul Menhauer, who was in Northwestern. And even though you may know everything that there is to know about how 2 particles interact, this is classical mechanics, when you put all the particles and you bounce them up and down, something like this happens. If you look from the top, you can have all of those phase structures that you see on the left. How do you make sense of this? Well, nonlinear dynamics is something that comes handy in here. Or you have particles all identical, you put them in something like a shallow Petri dish instead of the long cylinder. They were all identical, the white and the blue were identical. You rotate it and you produce this. This is from our own work. How do you make sense of this? Nonlinear dynamics, the picture at the bottom can tell you something about this. Or, can you model this? Yeah, you can model this. Then, this is an example coming from our work.
You're saying those particles differ only in color?
No, only in size. Only in size. If they differ only in density, the same thing happens. They can differ also in shape, and something similar happens. So there are tons of examples having to do with self-organization coming from this very humble, granular stuff. And in some questions about the granular stuff, these agent-based models come handy. So for example, if you pour in between 2 parallel plates an initially well-mixed collection of particles, red and blue, which in this case they differ by shape. Some of them are more compact, some of them are more elongated, okay? As soon as you pour them, they stratify in this way. And you can understand this with this second tool, agent-based models, to some extent. You can also, with agent-based models, understand a little bit about how segregation in cities happen. What I show is the 0th order approximation. But you can also explain with rather simple rules how termites organize, forming these colonies. So another simulation in NetLogo is this one of the termites. So you have termites, which are the yellow thing here. Sorry, the termites are black, and you cannot see it. This food that these termites have, wood chips, which is the yellow stuff. Okay? So this is initial state, and you control 2 things: the number of termites and the density of these wood chips. And you let the program run, and it does this. Okay? Now, how on earth this happened? Is there a central termite that is the organizer of saying, I want a circular mound built in there? No, the algorithm is more or less like this. This is the algorithm. And this is why it's important to know that these things can emerge with very simple rules. The idea is that all the termites work randomly. When one hits a good chip, it carries it until it finds another good chip and puts it together. And another termite can come and take a good chip from there, but the truth is that what happens is that if the piles start getting bigger, they can only be eaten from the sides. So some big piles start growing at the expense of little ones, and at the end you are going to have one final pile. This can explain flocks. By now, it's pretty much agreed that when you see geese flying, there is no central commanding geese. The one at the front changes all the time. However, the V formation gets connected. And from this, to study how unmanned vehicles organize robots, it's only a short distance. The question is, how do you maintain cohesiveness in flocks with no central authority? Like this one, for example. So some of these things have been investigated, and if there is central fish in there that is giving order to all the other ones, no. So from this, in the area of agent-based models, you can go from the humble granular stuff to traffic problems. So for example, this fellow Dirk Helbing in Germany has analyzed things at the intersection of traffic, pedestrian traffic, granular stuff, and granular materials. And I would recommend going to that website. And there are even books or proceedings with titles like Traffic and Granular Flow. Another problem which is very interesting is this one. There is a central colony of ants. And there are 3 sources of food. And the question is, how do the ants go and look for food? And if you take a snapshot, I took this snapshot at the moment in which one source of food has been completely depleted, the one that happened to be the closest. And now they are going with a vengeance for the second closest source of food, and eventually will go to the other one. How does this work in here? Well, this model is slightly more complicated because the ants start working randomly, but while they work, they release some chemical trail, a pheromone, okay? And the pheromone can diffuse and evaporate, okay? But the ants are trained to follow this trail. Once some of them have hit a source of food, there is a reinforcing mechanism in which other ants will try to go where the trail is, and even though there is no central mechanism to tell them, go to the closest now, to the most distant at the end, this is what happens. So ants are a very popular thing in complex systems, and there are even algorithms. France Telecom uses some of these to route calls. Now, people in operations research don't like this because it's not very precise. It's sort of heuristic. But it works for some of the things. So going back to this, could you design building blocks, designer building blocks, that would allow you to build what you want to build? And this is at the beginning. And the truth is that the models on what kind of structures get created with building blocks, molecules or colloidal particles that you engineer in some way, is very much at the beginning. And even if you want to know what will happen when you throw molecules like the ones that I'm showing here, these are all possible combinations of 4 atoms Some of them are neutral, some of them are positive, the blue, and some of them are negative, the black, okay? And you throw them and let them organize and go to a minimum state, energetic state. This is pretty recent. This is work from one of my colleagues, Mark Ratner, who is in chemistry, appeared in the Proceedings of the National Academy of Science. And I'm not going to go in too much detail, but in there you have what would be the emerging structures that get put together on an agent-based model prediction, or what will be the most popular will be a Monte Carlo one at sort of comparable stages of time. And the agent-based clearly is better in here, but this is something that is kind of coming up right now. Now, some people, this is another one of my colleagues, Bartosz Grybowski. Bartosz is working with sort of molecules, and let me exaggerate in here for emphasis, that you can see. So he's building little particles, in this case spinors, that are floating on the surface, in which he can control the attractive and repulsive forces. So these particles are magnetized, and if you are putting them floating, they will all clump together. But what he can do is make them rotate. And when they make it rotate, they repel each other. So he can control, with a central magnet, the degree of attraction and repulsion. And so these atoms, quote unquote atoms, can self-assemble in different configurations, which I showed there at the beginning, sort of lattice-like things. So he's building these systems from the ground up, and he calls them dissipative self-assembly, but conceptually similar to just letting molecules come together in some particular way. Now, on the network side, this is another way of looking at the world, and what I will advocate is that part of this should be deeply embedded in the education of people in engineering, for example, because they will be able to attack more problems than they currently can. So networks basically are ways of looking at things very closely connected with graphs, on which there is an enormous literature coming from operation research, in which there are nodes that could be grains, genes, proteins, neurons, people, okay, organizations, cities, and they are connected in some way. So, for example, the genes by some cross-regulation, the neurons by some signaling mechanism, species in an ecological system by some trophic relation. And the question is, in what way this can sort of sharpen our thinking? So this example is one that, it's a toy example, comes from Luis Amaral, who is in Northwestern, and is an example about the diminishing of cod in the Northwest Atlantic, okay? There is a quota that you give for this, and the quota is adjusted on how many you caught the previous year, and so on and so forth, and it was going down. So people tried to find the reason for this, and the poor seals, the harp seals, were blamed for this. The harp seals are one of the factors impeding the stock rebuilding. Now, so when you do that, you can think about what the food chain will look like. And so you have the harp seals at the top of this, eating the cod, and the cod feeding on some stuff at the bottom, crustaceans or something like that. Or you can make it more elaborate. There are several kinds of crustaceans. But when you go and look at all the ecological relationships, and I'll tell you, when ecologists study something, be a lake or something, they study everything, okay? So when they look at all the relationship between the species in the Northwest Atlantic, this is the real web. And this is where the harp seals are and the cod are. Now, if you tell me that what will happen when you change one species as to be able to predict what will happen with the rest, it's impossible. This is a very highly interconnected system. Network theory gives you some ability to deal and organize this information. And as I'm saying, this is a tool that people in engineering should have. Now, can you make sense out of this? Well, if you look at it as a system with many, many degrees of freedom, many variables, statistics starts playing a role, and you discover that many, many ecological systems have the same kind of distribution, for example, of predators and a whole bunch of things. These are for different, there are 6 examples coming from different parts, lakes, different pieces, ecological systems studied in detail by ecologists, and this is a very active area. Of course, the ultimate network is the internet, okay? And this is a snapshot of the internet, and the questions in here, the same as in the ecological system, is what happens with failure in one location, how failures will impact the system if they are random attacks or targeted attacks. The white spot there, by the way, is very close to Chicago. Okay? The internet is always failing, but it's always working. So how robust are to 2 things, targeted and random? So all of these impacts national security. It doesn't have to be internet. It could be a supply chain. It could be a telecommunication network. Could be something else. Could be a transportation grid. And these transportation grids are something that has been studied in detail. Again, Luis Amaral is one who studied this. And I'll give you one study that he did about the worldwide transportation, air transportation network. So to give you a sense, there are about 2,700 daily flights out of O'Hare and about 700 million passengers moving every year, okay? There are more than 800 airlines, large and small, and 500,000 flights between 27,000 pairs of cities. This was in 2000, okay? Now, what are the most critical hubs? It may be that the ones that has the most flights per day is not the one that will impact the system the most. For example, Frankfurt has more flights than Paris, but Paris is more important in disrupting the rest of the system. And you have to define disruption. Now, the reason that this is very, very important is that if there are epidemics, the epidemics move along the routes. And a case that was looked at by these people was the severe acute respiratory syndrome, SARS, and how with a few connections you can get things moving from one place to the other. Just as curiosity, if you pick any 2 cities at random in the world, it takes an average of 4.4 flights to connect any 2 of them. Okay? Obviously, pick Chicago, London, or New York, Chicago, it takes 1. The one that took the most number of flights they could discover is, and this is the beauty of having the tools to analyze these things, it was from Mount Pleasant in the Falkland Islands to Wasu, Papua New Guinea. It took 15 flights to get in between those 2. Similar things apply. Either may well be that you want to disrupt a metabolism, cell metabolism, or you want to shield it from something. In here, if you look at it as chemicals and which one plays with which, you can get the graph on the right. But if you look at that 3 species have to come together in a particular part location to produce 2 more, okay, then the graph starts looking like this. This is work that I'm doing with Ashley Smart. So in some sense, when you look at the metabolic pathways in a cell, the graph could look like this. Like species B and C have to go to location 2 to produce E and F. And if you look at it in this way, it's pretty much like even a supply chain. It may be that 2 things have to come together to produce 2 more. And the question in here is, what kind of failures will produce if one of these nodes were disrupted, and you have what you'll call cascading failures and things like that. And again, you want to investigate, are there general ways in which things will fail? And this is all ongoing now. There are other aspects of networks. The oldest part is graphs. Okay? They have been studied for a long, long time. And one particular group of things that is very well organized is synchronization. This is an old problem, comes from Huygens, the one discovering that two metronomes were synchronized or two pendulums in the wall. But how there are some fireflies that flash all at once in some regions of the world, how circadian rhythms get kind of in phase, how happens to be the firing mechanisms of neurons in the brain. All of those things form a subset of this network part of complex systems, which is pretty big. And one book that I would recommend is this book, Sync, by Steven Strogatz, who is at Cornell. Now, statistical mechanics. I kind of, in passing, mention when I show distribution coming from ecological systems and I drew curves, something along these lines, that you can make sense out of these things because there are so many elements into the picture. Now, statistical mechanics is useful when the number of degrees of freedom is large, and in some cases, in examples similar to the ones of Schelling and the cities, you can solve them almost analytically. The most celebrated is the Ising problem. And something that gets used in here are Monte Carlo methods, but sometimes they are not good, as I show in the previous example of self-assembly of atoms, and fluctuation. Fluctuations are big in statistical mechanics. And a very recent hot topic in StatMech has been connecting with networks. But fluctuations is something that is very big. So the normal kind of fluctuations that one is used in traditional things is like Brownian diffusion, in which all jumps are equally probable in whatever direction. But that will be what is on the left in there for you. But there are other kind of fluctuations that are more what you will call have fat tails, in which once in a while there are fluctuations that are very large. And this has become really another big industry. There are books and conferences and the area of econophysics. For example, fluctuations in stock prices and that kind of things. Can you predict a crash before it actually happens? Is there a signature that would reveal that something is about to happen? So this is a big industry in this, and if you sort of Google econophysics, you are going to find a whole bunch of things, and a lot of them have to do with application of statistical mechanics to social problems. Now, a bit of history. Two things. The first one is that the fellow who coined the term condensed matter physics, Phil Anderson, he came up with a term in an article in Science 1972. He basically was saying that things like critical phenomena cannot be understood by looking at individual elements. Just changing the number of elements was in itself something that led to qualitative change. And I mention this because this was 72, and he would have understood most of what we are talking about in here. But even going earlier, John von Neumann, who his first degree was in engineering, who was from Hungary, he would, more than anybody else, he could be imagined as the father of cellular automata, and agent-based models could be traced back to him. But let's go even further than that. The father of statistical mechanics is Maxwell, and his insight was to more or less say, we'll give up the notion that we can calculate individual trajectories. He was following the footsteps of Lagrange and Newton, and we have to argue for distributions, averages. Now, if you go and read what Maxwell wrote when he was arguing that this was a reasonable thing to do, which by no means was something that people would accept just because he said it, the examples that he was using, we are talking about one of the pillars of modern physics, okay, Maxwell. The examples that he was using were coming from people like this. This fellow Quetelet, before Maxwell came into the picture, they were trying to build models of social dynamics because they were so enamored of the success that Newton had had in physics. And so one of the things that, for example, Maxwell was surprised, arguing for constancy of averages, in England people were fanatic about keeping track of things. They will even count how many letters in a given year were improperly addressed and couldn't be delivered. And the percentage was almost the same every year. So Maxwell was giving examples like that from sociology to develop physics. Now we are going kind of the other way around. We are using Maxwell to apply things to economics and social problems, which in some sense sounds strange to many people, but if you go and read about this, you will find it all in there. A book that I recommend is this book, Critical Mass by Phil Ball. Phil Ball was one of the editors of Natures for Physical Science. Now, as to engineering, why on earth, if this is so good, has not caught fire in engineering? Okay? What's a conflict? The conflict in my mind is that the hallmarks of complex systems are adaptation, self-organization, emergence. Okay? No one put together all the internet. No one puts together an ecological system. They are there. No one puts together the power grid in the eastern seaboard of the United States. Engineers like to engineer things. They like to build everything. They are much less adept by training in dealing with something that is already there. But if you want to deal with what is already there and make sense out of it and study how robust it is, you need to have tools. Engineering, in some sense, historically has dealt with complicated problems rather than complex problems. And my message in here is that we will be much better served if we increase the range of problems that engineering can and should attack. But this is probably not very easy. This is adapted from a famous article in a Harvard Business Review. It's about the growth of organizations, and several years back I adapted it to the growth of disciplines. So at some moment a discipline gets created, and it's clear what this discipline is. And there are people who are sort of banging at the door of this discipline. We would like to get in there. So take, for example, chemical engineering. I do not know how many of you are in here from connected with chemistry. How many? Okay, good. So at the beginning, biology was banging in the door of chemical engineering saying, we would like to get in. And the answer was, no, it's not well developed enough, and this and that. And at some point, when you are at the top there, the pieces have become so big that now it's in the best interest of the discipline to try to capture the pieces that are with the risk of flying out. So what is happening always is that there is some state of the art of what each discipline imagines itself to be. And if you have a breakthrough, by definition, breakthrough means break with. You are breaking through the boundary. At some point, the things either splinter or sometimes the discipline can adapt the thing in there. But at any given point in time, this is not showing well in here, but you have a core of what constitutes doing well, being well grounded in a given discipline. And there are little pieces that are attached to this core that eventually may become part of the core or may not become part of the core. So there is always a battle in between what is more conservative in the middle versus what is more revolutionary in the periphery. The question is, should engineering in all of the disciplines adapt some of these, or should be a different thing altogether? And this comes to the question of, should this be multi or inter? Multi, according to the dictionary definition, is something that makes use of different disciplines at once. Inter is integration. And that's the challenge, because that's where the value is, in my opinion. Now, what are the barriers in here? Each of the disciplines that forms part of this, ecology, operations research, physics, sociology, whatever, they all have their own languages, mindset, cultures, academic silos. They have different rules about expectations, practices, and they all have different rules at what constitutes even proof in different disciplines. So by no means putting this together is an easy task. So just to go through the first three there, engineering, as I argued at the beginning, you have to solve problems with whatever tools you have at hand. You cannot say, I will not solve the problem. If all the science that you need is already there, it's your obligation to use all of it. If gaps remain, you have to fill it somehow. Okay? But that's a different mindset than in math, in which things are a forever kind of proposition. And the mode of working is very different than in physics, which is more observational. And when you start putting all these disciplines together, you have to be aware of what sort of reference frame they are using, because what you may be disagreeing is about these deep-seated beliefs on how the disciplines are. So what I also believe is that some of these elements, and in fact this is why I decided to do something in Northwestern that was integrative, was the question that we asked was, what at this moment in time could serve as a vocabulary? You look at all the university and all the different pieces. You have medicine here, law, engineering, business, communications. The question is there some kind of shared vocabulary that people can use to communicate and present problems to each other, such a way that you lead to something synergistic where value can be created just because ideas could emerge from different camps. And we settle on complexity as being one of the possible answers for that. So I think that the people who are well-versed in this, and even the tools that I mentioned, agent-based modeling, networks, they serve as cross-linkers of disciplines, and eventually create new disciplines. So on the educational side, I'm going to make the claim that, and I would like to see undergraduates exposed to at least agent-based and networks. I think the entrance price to know something about that and make sense is relatively low. Remember the low threshold, high ceiling of NetLogo. I would say that this is what is in the toolbox. Most of the people who work on something having to do with complexity, at the end of the day, when you ask them what are you using, will fit in one of these 4 categories. Now, once you give people tools, they can attack problems. So if you have problems, they need some tools. And the question is, do you look at problems and decide what tools you should have, or you equip people with tools, and then they look and hunt for problems? So at the beginning, when you are deeply interested in solving some problem, let's say the problem of the harp seals and the code, and you start saying, what would make sense to do here? Probably you will have to settle for the inescapable fact that when you look at the ecological network in there, you better know something about network theory because there is no other way around it. I mean, how on earth are you going to make sense out of that? But once the tools get embedded into a system, there is not knowing what people will do with those tools. So I think there you can see them as enablers. And eventually, who knows if there will be no more departments of systems engineering around. There are a few, but probably there could be more. So the central message is that engineering can benefit by the incorporation of complexity tools in the middle or in the standard toolkit. Now, what's out there? I try to give you a bird's eye view of things going on from here and there, but the range of things is enormous. It goes from sociological problems, structure of organizations, and how putting the structure different can lead to more creative work or even more effective product design, to social networks. I'm throwing some names in there, like Watts, who is in Columbia, Strogatz is in Cornell, Milgram was the inventor of the small worlds, used to be at Harvard. Problems connected with cyberspace and web. Barabasi is another Hungarian fellow who is in Notre Dame. Huberman, who was in Xerox. And once you, for example, lots of networks for a while, people discovered first that they were called what now is called small worlds. And now you go hunting for small world networks. And then you discover that there is another broad class, which are scale-free networks. And now you have two classes. And the question is, you have two options, either to classify this even if imperfectly, or to go to the state in which no network is alike any other network. Okay? So some middle ground in there will be beneficial. Systems biology is something that I kind of skimmed through, but Lee Hood in Seattle has been the main proponent of this. Propagation of viruses and so on, epidemics, that kind of thing. And viruses, even internet, it's something that gets captured by this. But going to more concrete list of problems in engineering, they are not classical problems. Ecological systems, I think people in engineering should be the ones looking at many of them, because as a foundation, they will be well equipped if they learn some new tools to deal with these things, obviously not by themselves, in teams. Sustainability, there is no question that some elements of these have to play a role. I mean, we are dealing with systems that are highly interconnected. Epidemics, which is not something that is in the center of engineering, should be even what to do if. There was a big study about Portland and what would happen if anthrax, for example, would be released in Portland. Los Alamos did this. And the question is, how do you go about analyzing this? And the answer is, you need some tools, some of which probably have to do with very sophisticated agent-based models. And then systems biology, which is something that people in engineering are already involved, and self-assembly, which, as I told you, it looks simple, but is one of the most complicated things to crack. And it may well be that some collection of problems, for example, how to deal with enterprises and natural disasters, or weather disruptions, or congestion, or any kind of failure, or disruptions of any kind, all of these eventually could be bundled in something that would acquire a different name, like security engineering. The name is already taken. The fellow Ross Anderson in Cambridge has written a lot about this, but they are not exactly courses in security engineering involving all of these things. A lot of them could be supply chain disruptions, for example. And in order to understand that, probably you have to understand something about networks and so on and so forth. my point in here is that once the things move, because the tools are there and there is enough work, there could be bundling of some things with new names, some of which I really cannot imagine. So this is a very, very egocentric list of papers. I put 3 of mine because I borrow a lot from myself. One of them is very, very short. It's about a page and a half, the third one in there. And there is one book that I will recommend, and it's the book of Phil Ball. So, as I said at the beginning, it's very hard to put in a unified, useful way things that have emerged from many different sources. I could argue that some of the things, this is the best way to see them, but this is a system that evolves, and eventually some viewpoint becomes the most prevalent. As I said, I try to give equal attention to what I think are the elements that at the end of the day are in the toolkit of people looking at things that they are called complex. With that, I will end. Thank you.